this distribution, the structure that we want to find here. Okay, and so that's what the class is going to be about. How do we layer on more and more observations? As we get more, we get a better estimate of what's going on here in a variety of ways. Okay, so to kind of, in this lecture, we're going to start with a fairly simple system. We're going to assume that each xi is going to be in this set, instead of n, let's call this m. Okay? And so this is just going to represent this notation with the square brackets around m means the numbers 1, 2, up to m. Okay? And so it's just a simple way of representing this set. And there's nothing special about the numbers 1 to m. This can represent things like all IP addresses. You know, it could be like all, you know, like all possible words. So it used to be you would think of all possible words. Well, the data we collected on language was like there's this data set from like the New York Times, and they spell checked everything, and they had these grammar rules. And so all possible words were the words that New York Times allowed into print. But now we get data from Twitter, and people don't spell correctly. They use weird abbreviations. Sometimes it's just nonsense. So all possible words could be different now. But it's some big number m. Okay, I don't know how big it is, but it's some number m. Or it could be something simple like the number of days in the year. Okay, and in this case, m would be 365, or 366 in 2020, right? Because it's a leap year. Okay, so it could be these things. Okay, and so this is the so this is going to be the domain, and then we're going to analyze a known. So a known distribution. Now, we're going to know this distribution, and this is going to be, this one's going to be uniform. So that means that the probability that xi equals j equals 1 over m. Right? There are m possible things it could be. So for the ith observation I make, the probability equals j for any j in this set at m. Okay, so for any element in the set m, so let's say today is January 8th, right? So if this is January 8th, right, then it's 1 over 365. This is the day I chose. Okay, so we're going to start with this simple uniform distribution. And so this is some process, and what we're going to do today, instead of having an unknown process, we're going to look at this known process, and we're going to analyze if we look at draws from observations, how close do we actually get to the true, so like uniform distribution. And we'll see that with the small number of samples, a lot of weird things happen. It's not perfect. We're not getting like it might not be what you expect to happen with the uniform distribution with some reasonably small number of samples for different values of what I'm asking to be small. When you get to like when the number of samples you get to be like 1,000 or 10,000, it's going to start to look uniform. But for things kind of less than that, especially with m equals 365, maybe some strange things are going to happen. Okay. The other thing about this distribution is that it might seem kind of simple and strange, but this actually comes up in algorithms and data structures a lot. This is basically like what's going on in hashing, as in So like if you use like a hash table data structure, then this process is what underlies the hash table data structure. When you get in a new item, right, when I make a new item, I put it in the hash table, it's supposed to map to one of these random m spots in the hash table. Okay? So how many have not heard of a hash table before? Okay, so that's this is probably, I'm not going to really review it so much, but it's a quick way of storing sets. It might be something good to kind of look up to kind of get an understanding of data structures. We're going to use hash tables and this sort of hashing later on in the semester, inside of some other algorithms. Okay, so all right. So what is and I'll call this a random, hash function. So this is something that you won't necessarily have to implement this for the first assignment I just showed you, but in the second assignment, you're going to need something that's going to work like one of the hash functions used inside the hash table. For the first assignment, you can just generate some random numbers, and it's fine. But we'll need to use kind of actually these properties, these hash functions, in the second assignment. And so the hash function, so it's important to kind of review what's going on here. But this is kind of part of this random process. It's kind of related to the random process I just described it. It's the kind of the backbone behind these hash tables, right? So, and I call this the random hash function. We'll see in a few lectures in a couple of weeks a locality-sensitive hash function, which you probably have not seen before. But just to distinguish between the locality-sensitive one and this random one, I'll call this a random hash function. But this is like these uniform hash functions and so forth you may have learned in a data structures class. Okay, so this will be, we'll have some function which maps from some sort of domain. So any function maps from a domain to a range, right? So this is the notation for a function where this one maps from and to, and we're going to map it to this space M, this set of these M numbers. Again, these can represent anything, but we'll just keep them as the M numbers because the notation is simpler here. And the domain, generally will take in, say, some string. You might have seen this the string notation or something else. Think of it. It could be a number. If this is confusing, just think of it as a number. There are ways to convert strings to numbers. Okay, or it could be a string represented in binary in some way, which is kind of like a number. And this function, even though I'm calling this a random hash function, this is deterministic. Okay, so this means if I have a hash function, it's going to map from any string into one element of this domain. Yeah?
I can't really tell what this is the string that you put up there. Is that sigma?
Yeah, good. Right, so I wrote up here, this is supposed to be if I write this in so like LaTeX, this is sigma, it's uppercase sigma, there's some family of characters, and then I have k of them for some value k. It's not too important what the input to this is. There's, I'll mention how to implement this, and for most of what you'll do, you'll use built-in functions, and they will allow you to pass in a string or a number or something like that. I just want to put something there for the domain, but it's not too important. But thanks for asking. If my notation is not clear or the writing is not clear, please stop and ask. Yeah.
Yeah, I was going to say, is that the set of strings over an alphabet? Or?
Yeah, so it's a set of strings over an alphabet. That's, this part's not so important. Okay. Yeah, don't sweat that so much. Okay. Okay. Okay, and so this, once I have a hash function, it's deterministic. That means if I get the same string or the same number, it will map to the same location. Okay, in a hash table, this is important. But what's going on is you randomly select H. I'll call this. I think my notation is HA. Write this. HA from some family. So this is supposed to be a family of hash functions. Okay? And so if, and they should have roughly have the property that the probability of HA of, let's say, of X equals HA of Y equals 1 over M for X not equal to Y. And this probably is taken over this choice of, now I'm selecting this HA from this family of hash functions. Okay, so when I talk about when you talk about probabilities of hash functions, that's the choice of the deterministic function. The function is just some map, right? It's a fixed map, but you're choosing a random hash function, and the random choice is usually all denoted by this variable a here. So if I have a and a prime, then those are different hash functions, and that a parameter is what distinguishes them. Okay, so how do I define these hash functions? I'm going to talk about 3 different versions. So the first one, and I usually recommend you do this, is like a built-in hash function. Python has dozens of built-in hash functions. Almost any programming language has built-in hash functions. A very common one, which is not state-of-the-art anymore, like Python 3 has SHA-1, but it has like 7 other versions of SHA, which is this kind of cryptographic family of them. And so SHA-1 is probably a built-in one into just about any reasonable language. This is a cryptographic function that can take in a string and which has a domain which is binary, right? And so it's going to take in this, a string of length k. K can be pretty big, and it usually maps to a domain of m equals 2 to 160. It gives you 160 bits. Okay, and if you don't want all the bits, you can ignore some of the bits, and then you get a smaller domain. Okay, and so this is a fixed function. How do I draw one object from this function? The way I do that is that A is going to be a salt. So I'm going to take as input, so if my input is X, then what I'm going to do is I'm going to call SHA-1 of the concatenation of X and my salt. Okay, so for different choices of A, I get different hash functions. So if I chose A randomly or just arbitrarily, more or less works fine. So if I want 10 hash functions, I can use as A the string 1. For the second hash function, use the string 2, and so forth. And this basically works fine. Okay, and this will give me, you shouldn't be able to distinguish between the outputs, which means they roughly don't intersect, or basically random. Okay, and so this is probably the easiest way to implement a hash function if you want to implement it. Okay, inside a programming language. Okay, and you don't need to use SHA-1. You can use any other built-in hash function. There are probably easier and nicer ones built into any of your language. Yeah.
So you're saying they're built into the libraries of most programming languages?
Yeah. Yeah. So Python 3, look up SHA-1, and it'll say, well, there are actually 7 different versions of SHA. SHA 256, and so forth. Yeah, but if it's like Java has a lot of other built-in hashes as well, you can use any of those. They'll all basically be fine for this class. There are some technical details when you want to use other ones, but that gets pretty deep into the weeds. Okay, if you do want to implement it from scratch, okay, there's a fairly simple technique which works reasonably well. Like for most scenarios, this is fine. It's not going to be called multiplicative hashing. This one's not going to take in a string. You're going to have to take in some sort of number. So you have to first convert your string to a number. But it's defined h of a of x is going to be m, which is the size of the domain. So the fractional part of x times a and the floor of this. Okay? So the fractional part, frac of 17.32, this is going to be equal to 0.32. It's the part after the decimal. Okay, so this gives me a value between 0 and 1, multiplied by m. Now it's a value between 0 and m, and I take the floor, and it's a value between 0 and m minus 1. So now I've gotten in between 0 and m minus 1. If I actually want to start counting at 1, I can add 1 to it or not, right? The typical start at 0 or 1 issue. Okay, so if you want to implement yourself, this one is safe to do. And sometimes instead, what's a faster way to implement this is x times a again, divided by 2 to the q mod m, where q is where q is some large number. Okay, you can kind of do this too. This kind of works as the fractional part. You can get this to implement with bit shift operations if you do this right, and this can be a bit faster. Yeah.
X sub a?
No, this is just x times a. It's the same thing as up here. This is kind of replacing the fractional part. You can implement this a bit faster, it turns out, but if you really want to detail it, you can look beyond my notes to figure out. Yeah.
Sorry, are those? It looks like there's a left parenthesis and then another left and then just one right. Am I reading that wrong?
This is a left paren. This is a divide by.
Oh, okay.
Yeah. Divide by 2 to the q. Yep.
When you say large number, roughly what does that mean?
Oh, yeah, it depends on how deep you want the answer. So to be I mean, if it's like 2, it's not going to work. You want to do something that's going to basically raising it by 2 to this is going to kind of like shift it down. So like basically I'm multiplying by something to kind of turn what I've done into a much larger number here. And then I want to take the fractional part. And so this is kind of turning everything into the it's kind of doing something like taking the fractional part. So I just want to divide by I don't know, probably something like 10, or like it's 2 to the q, I guess, should not be too much bigger than a. But so if you don't want to dig in the details, just implement the version in blue. And then if you really want to speed it up, you can look at these variants online. But they aren't going to be too important here. I want to get into some other stuff. Yeah.
What is M exactly?
M is the domain that you're hashing into. So I want to hash into between 0 and
Okay.
the number of IP addresses, and the number of IP addresses is going to be M.
Right, the number of the set.
So
Yeah.
is the, in this multiplicative hashing, is the A referring to the same salt as C?
Yeah, it's the same salt. A is the same salt
And
and the same.
is that just kept, is that something you just pick and then keep the same, or is it different?
You pick it for each hash function, which is deterministic. It's fixed. When I pick, later on in class we're gonna need multiple hash functions, and so I have to pick a different A for each one. For today, we'll effectively need like one hash function, but later we're gonna need multiple hash functions.
So then for built-in hash functions, is that A is predetermined by like Python?
No, A will be chosen by you. That's what you choose, and if I want 100 hash functions, pick the numbers 1 through 100, right, as your salts. That's going to work fine for doing concatenation.
So can you manually change the salts for the built-in hash functions?
You have to manually add in concatenate your input with it.
Oh, I see.
Right? So you are manually concatenating. The hash function itself, SHA-1, is a fixed function. Right? There are other ways, there are other things where you set the salt within it and various implementations, but if you want to just use SHA-1, which is everywhere, you need to do manual concatenation of your input. So if I have two hash functions with A and A prime, I concatenate one with A prime, but I pass them both into SHA-1. Okay, and that effectively changes the hash function, and they should look, indistinguishable. Okay. Yep.
So do we pick M in this case for the multiple?
Yeah, the M is what you pick. That's the domain you want to map into. Okay. Okay. So one of the reasons I want to write up multiplicative hashing, and you will not need to implement this for the class, but you can if you want to, is that there's like this other version of hashing called that's called modular hashing, and so the real reason to put this up is that modular hashing is h of x mod m. Okay, do not use this. Okay, it's surprisingly common. You see people using this. This will occasionally lead to some weird problems. This is not a good hash function. Sometimes it'll work fine. Other times it'll cause problems. And I run into people trying to use this all the time. If you want to use something like this, do multiplicative hashing instead. If you want to write it yourself, do not implement modular hashing. You will run into some issues with this. I really recommend just using a built-in hash function. Okay, the built-in ones are probably optimized to work faster. Not SHA-1 necessarily, but some of the other ones. Yeah.
Why would we make our hash function instead of using the built-in?
Some people want to. Okay, if I don't explain it, I'll get asked about it. So I just figured, okay, I'm gonna explain it. Okay, there's sometimes you're like, why is SHA-1 so slow? Can I speed this up? You can use a different built-in hash function, or you can do your own, and this is a pretty good choice. There's a whole lot of research in optimizing these things. Sometimes we'll need other properties of hash functions that you won't necessarily be able to guarantee with the built-in ones. They mostly are beyond the scope of the course. But they may come up in questions later in the semester, and then I would say, well, you can do something like this.
So which one do you personally use a lot?
I've been using for like 20 years this one called the Mersenne twister, which is this cryptographic function that had good code for a while. I think there are better ones now, and a co-author of a paper convinced me to switch to a different one. I don't remember what it is offhand. Okay, but the Mersenne twister is what I had been using. Or I'd use whatever some built-in one from Python or something else. Yeah. So, all right, okay. So we kind of know how to do this. For the for this experiment, I mean, in this, for your homework, what you can do is you can call like a uniform random value between 0 and 1, and then I can do u times m, and I can get the floor, and this will be some value j in this domain here, right? So every time I generate a random number, for the first homework, you don't need that the hash function is the deterministic process. We'll need that later on, but for now, for your homework, you can just do this. Okay. Okay. So now I want to talk about this process. Okay. So this will be just kind of to represent some of the sort of phenomena that happen in these random process, and so I want to ask a couple of questions about kind of if we keep generating these random values in this domain, and what happens. And the first question is how many samples x1, x2 up to xn. So any 2 xi equals xj. Right, so these are going to be all in this domain of size m. Right, so how long until I get a collision? Right, so how many do I draw until I have a collision between two of these things? Does anyone have a guess or know the answer?
1 divided by 365 squared.
Okay, so guess 1 over m squared times m, and this would be 1 over m. Right, so maybe roughly 1 over n, maybe 1 over n times 1/10 or something, right? Maybe roughly maybe it's saying roughly, if I wrote in big O notation, theta of m samples, right? So theta of m samples is a reasonable guess. Something like that. Any other guesses?
No guesses. Answer.
23.
It is known as 23.
Okay, right. Okay, so the birthday paradox, you're jumping ahead a little bit here, is going to be a number about 23, but asymptotically, what does 23 mean? Like if instead of days of the year we lived on Jupiter or something that has I don't know how many days there are in a year on Jupiter. Let's say there are 1,000 years. Is it still going to be 23? Or is it 42 then?
23 is where you hit the chance of having about 50% chance of two people.
Yeah, so I'll go through this analysis. Yeah, so more formally, about how many do I get until I have a 50% chance that I will have seen a collision? How big does n need to be? We have a guess of roughly m. I can throw roughly m things in there asymptotically before I see a collision. Hash tables work, right? People use hash tables, so that might be a good guess. You have to deal with collisions in case they happen, but so it turns out the answer is going to be n of roughly. So I'll put something like this of square root m. Roughly square root of n. So that's a lot. With 23 is roughly square root of 25. Maybe square root of n times 2 might be a little bit better. But
So is this a uniform distribution?
yeah, this is the uniform distribution for this. So we'll just look at this. I can talk about if we change from uniform afterwards. But okay, so this is, yeah.
I was just going to ask the answer to that one second question was just square root of n.
Yeah, so it's roughly square root n. And I'll go through the analysis to show you why it's not too hard to get a good to actually derive where this square root n comes from. Okay, so how many of you have heard of the birthday paradox? Okay, and how many of you have done a simulation of the birthday paradox before? Okay, good. So not too many. Okay, so here's what we're going to do. The birthday paradox is this. Someone went on David Letterman or Johnny Carson once and said, the audience had about 50 people in the room, and they said, I'm willing to kind of bet that two people in this room share the same birthday. I don't know anyone in this room. I believe there are only 50 people in here, but I believe two people have the same birthday, and they didn't believe it, so they went and asked everyone, and they found two people with the same birthday, and like the home audience was very amazed by this. Okay, and so it came to be known as the birthday paradox that's going on, and we're gonna simulate this in class. We're gonna see how many. We're gonna go through you randomly, and we're gonna see how many of you it takes until we have a collision. Okay, so we'll go through, and everyone will say their birthday. If you don't want to reveal your actually birthday, you can choose another day in your head right now, but don't change it. Okay, I don't want any funny business here. And okay, so and then are there any twins in this room? Okay, so no twins. My son has two pairs of twins in his class right now. So he did last year, and they were different pairs of twins. So okay, so aside from twins, it should be roughly a uniform distribution. Okay, and so we're just going to go, and we'll see how many it takes to get a collision. And I've heard about 23, and I'll argue that there's a pretty good chance, high probability we'll get there by 50. So it shouldn't take that long. Okay, so we'll just go, and let me pre-process this a little bit. April, May, June, July, August, September, October, November, December. Okay. October 13th.
November 24th.
24.
December 21st.
First.
March 23rd.
March 23.
November 23rd.
November. What did I hear? A collision already? Okay, but that's not the same process. We're going to go up here. Okay.
January 26th.
January 26th. You can answer too, Benway. You're in the room. Benway is one of the TAs. So. January 12th? Yes? Okay. January 12th.
October 24th.
October 24th.
May 4th.
It's Star Wars Day.
October 13th.
October 13th. Okay. I think this is the earliest I've gotten it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we had a collision after 9 steps. Okay, so it turns out that the probability of a collision is going to be greater than 0.5 after n equals, I think, 23. And I think, I think at 23 it becomes like roughly 53%. Okay, but we hit it after 9. I've done this in the past where we got up close to 50 before. So before it happened. Okay, so this happened after 9. Maybe this little group had a collision. Okay, good. So it's a random process, right? I expected 23. It took 9. Is this, did we break something, or was this reasonable? Okay, so let's actually go through the analysis here. Okay, and so I want to say the probability that a collision on a domain M after n steps. Okay? And so let's start with n equals 1. Then I know that the probability is going to be equal to 0, right? I can't have one birthday in a collision. with n equals 2, the probability is going to be what?
1 over m squared.
1 over n, m. 1 over m, right? Because the first person, they just pick some random number. The probability that the second person matches theirs is 1 out of m possible, one of m possible birthdays. Okay, for n equals 3, it's going to be what? Okay, so the tricky thing here, it's going to be, well, so it gets, most of the complication of the rough analysis happens right here. There are going to be n choose 2 pairs, right? So this is n choose 2. This is roughly n squared over 2. Roughly n squared choose 2 over pairs. So in this case, 3 choose 2 is 3. So there are 3 pairs. And if any of those collide, then I'm going to have a collision, right? And each of them roughly are equally likely to collide with each other. And so, so the probability of having a collision is going to be roughly 1 over m to the power n choose 2, which is roughly 1 over m to the n squared over 2. What did I do? So, yeah, so, and so if I have, right, so this is, so what I want to do slightly differently here is I want to say the probability this is I want to say the probability so this is not right either, right? This is getting smaller the more birthdays I have. I want to say the probability that I don't have a collision is going to go down instead, right? So the probability of no collision, that's going to be equal to 1 minus 1 over m, right? And then every time I have a new pair I check, I multiply that times this probability, right? So this will be roughly n squared over 2. So it's roughly 1 minus 1 over m. So 364 out of 365, I don't have a collision, and then I have this many pairs that I check. And so the probability I do have a collision is roughly 1 minus 1 over m to the power n squared over 2. Okay, so as n increases, this this is a small number. This is close to 1, 364 to 365, but it's going to, when I multiply these together, anything less than 1, it's going to start dropping very sharply. Okay, and so now if I set n equals to roughly square root 2m, then what this looks like is 1 minus 1 over m times, this becomes roughly m up here, right? Because the n squared takes the square root, and the 2 cancels with this too, so I have 1 minus 1 over n to the power m, and this looks like roughly 1 minus 1 over e. Okay, so there's this term is roughly, so like, or is it e, or is it just e, actually? 1 minus, no, it's 1 over e. And e is 2 point, this is one of these simplifications you can do if m is sufficiently large. This looks like 1 over e. And so this means this becomes about, I think it's like 0.3 or 0.6, something like that. Okay, so roughly constant probability happens at about n equals square root of 2m. Okay? So this analysis is not exactly right for a few reasons, but I'll argue it's a pretty good kind of back of the envelope calculation here. Yeah.
Do you need to redo n equals 2 at all, or is that still one?
N equals 2? Oh yeah. So no. In the case of n equals 2, it's fine. But when you see n equals 3, you're getting more than one collision you need to worry about. And how do you handle more than the probability of a collision? Yeah. So it's what's going on there is n 2 choose 2 is 1, and it's 1. Yeah, so that's the probability of a collision is 1 over m. So I'm doing 1 minus 1 minus 1 over m, and the 1 minus and the 1 minus cancel, and I get 1 over m. Right? It's still okay. Yeah.
Is it not to the power of n?
But n it's n choose 2.
Maybe n choose 1, right?
N choose, yeah. It's 2 choose 2. So 2 choose 2 is 1. Right? Because I have 2 things. I have to choose a pair. There's only 1 pair. Okay. Yeah. Okay. So there's a couple things wrong with this analysis. One of them is mathematical. Others of them are actually part of the modeling process. Okay. There's one mathematical error here that I've made. Aside from that mathematical error, but there's even if I look at and I use n choose 2 instead of this simplification here, you know, if I did this 1 minus quantity 1 minus 1 over m to the power n choose 2, what's going to happen when n becomes 366 or 367? Or n is equal to m is equal to m. Yeah, there has to be a collision. When n, okay, when n equals to m, there must collide. This is called the pigeonhole principle from someone who had lots of pigeons. They had or n equals to m plus 1. If you have m holes for pigeons to live in, and you have more than that many pigeons, then there must be 2 pigeons in the same hole. Okay, there has to be.
So that means there's no replacement. There's no you're allowing duplicates.
I'm looking for duplicates here, right? Yeah. So this is an IID process. This is with replacement. IID is with replacement. Yeah. Okay. So, but the analysis says if I plug in m plus 1 up in here, well, it's going to be 1 minus a quantity that is, you know, it's 1 over, you know, it's m minus 1 over m to some big power. It's going to be a really small number, but it's going to be positive. I'm going to say there's a probability that I there's a probability that I don't have a collision, is what the analysis said, and so that's incorrect, right? Really, what I need to do is write the true probability looks like collision looks like n minus 1 over n, or is that m? N minus 1 over, this is a probability of 1 minus n minus 1 over m, then m minus 2 over m times m minus 3 over m times m minus n minus 1 over m. So the probability I get a collision on the second, on the third person is a little bit different because I know the first two did not collide. So now the probability the third person collides is m minus 2 over m. The probability the fourth person collides, given that the first three did not collide, is m minus 3 over m. Okay? You know, it turns out you can analyze this. It gives you a pretty similar answer. Okay, so the math is a little bit different, so I made some approximation here. You know, it turns out this is not a big deal, and we're going to ignore this. This is only a big deal when m gets very close, when n gets very close to m. For reasonable, when I typically find the collision, they're going to be very close to each other, it turns out. Yeah.
What's the last term?
M minus n minus 1 over m.
Sorry.
Yeah, that's okay. But there are actually other issues which are probably larger effects than this difference for most reasonable values of m and n. What are other issues with the analysis I did? Yep.
Birthdays are not in ID.
Yeah, so birthdays are not IID. Okay, so you look up statistics. There are more birthdays sometimes of the year than others. I think they're highest in spring, but the actual peak comes in like, the mode comes in like September or something like that.
October 5th? That's my birthday.
That's
the most common.
That's the most common one, is October 5th.
You can find at least,
okay.
You can find
Okay, so the mode is, now everyone knows, is October, not 15th, 5th?
5th, yeah.
5th, and that's, okay. And you can be roughly 9 months after something, after New Year's. Okay, so, you know, it's not totally uniform, but, you know, if you look it up there, it's pretty close. You can see differences, but usually it looks, you know, it's pretty close to that. Okay, what's another problem with the modeling? So what's special about this year? Is there anyone with a birthday on February 29th? Okay, so there's actually 366 because of February 29th, right? Once every 4 years, roughly, there's an extra day, right? So that changes it a little bit as well, and that might be a bigger difference than the mathematical error, right? And then there are also issues with twins. If we have twins, they probably have the same birthday, right? I mean, they could be right around midnight. You know, but so, you know, if you have twins, you know, then they're probably gonna have the same birthday, and that makes it also not, you know, not so it's like not IID either. Probably even siblings is not IID to each other, right? Because you're and in a way which might be different, but they're usually roughly spaced apart, maybe roughly 2 or 3 or so many years. But you know, the distribution is probably skewed. Okay. There's also certain things. I don't know if this occurs with people in a data mining class, but if you look at like people who are hockey players and who become like actually make the NHL in hockey. They tend to have birthdays in like September and October in the fall, because they usually were the oldest people in their class, and they were bigger than the other kids in their age group, and they gained confidence, and they ended up being selected to the kind of the clubs and so forth. So there's actually a skew distribution of players in the NHL because of this. So there's other skew in here, and we made this modeling choice of IA. And so I'm going to say, we'll do calculations, but also don't take them like super seriously either when they're talking about data. Okay, when we're doing algorithms like hash tables, we can probably control this. But with hash tables, they're not going to be exactly uniform probability. There's going to be some error. SHA-1 is not exactly designed for this. It's meant for crypto reasons, but then that crypto got broken. They fixed it with, somewhat fixed it with some other ones, but it's not perfectly uniform. Okay. All right, okay, so that's, say, about the birthday paradox. The next thing I want to talk about is how many n until we see all j and m.